Hello and welcome to this video of the mobile cranes lesson. We will cover three learning objectives in this lesson. We'll discuss the different types of mobile cranes, the process of calculating the safe lifting capacity of cranes, and the safety precautions of mobile cranes. Cranes have one main purpose, lifting heavy items. Some cranes can also be used for excavation operations like drag lines and clamshells. There are two main types of cranes, mobile and tower cranes. In this lesson, we'll focus on mobile cranes and cover tower cranes in a separate lesson. Here are different types of mobile cranes. Let's learn about each one of them, starting with the crawler crane. Crawler cranes are one of the heaviest cranes and are mounted on crawling tracks, which provide them great stability and good mobility in rough sites. The arm of the crane is made of a boom and possibly a jib to provide additional radius for loading. The boom and jib act in compression to lift the load with the help of strong hoist cables or lines. Telescoping boom truck-mounted cranes are much more mobile than crawler cranes, as they are basically a truck that can move between sites and the lift points. During the lifting and rigging operation, the truck crane is raised on its outriggers to provide stability needed to counter the lifted load. The crane operator is responsible to make sure that the surface below the outriggers is strong enough to support the weight of the crane and the lifted load. Also, there should be enough space around the crane to open the outriggers and have them supported on reliable and leveled surface. Once the crane outriggers are secured, the crane operator extends the telescoping boom and performs the rigging operation. The outriggers are very critical in mobile crane operation as they provide the stability against overturning during the load rigging. Just a little level angle can result in severe reduction in the load capacity of the crane. In the case of crane operation on a natural surface, the soil bearing capacity has to be checked to be enough to hold the rigging load through the outriggers. Regardless of the surface bearing capacity, it's always good to use steel or wood pads to avoid concentrated surface stresses and failure. Conventional lattice-boom truck cranes were extremely popular from 1940s to the early 1990s. With the advancement of all-terrain hydraulic boom crane technology, lattice truck cranes have waned in popularity but still have great and powerful lifting capacities. Lattice-boom truck cranes are ideal for steel erection, port and bridge work, and are known for quick line speeds. The lattice boom takes a long time for assembly and setup, but their lightweight, efficient truss lattice design makes them more affordable than the telescoping boom for the same load. Some newer cranes are designed so that the machine can set up itself without the aid of another crane. You can recognize a rough terrain crane from its only two-wheel axles, which make them versatile and very mobile on rough construction sites. These cranes are equipped with large, closely spaced wheels to support great stability and maneuverability. Some models can operate on surfaces with steep slopes up to 70% grade. Rough terrain cranes have also a funny name, cherry pickers. This name comes from the crane used in the Second World War to pick up bombs, which had also a slang name, cherries. Rough terrain cranes can be also equipped with outriggers to use in heavy loads. You can see in the top photo how its great maneuverability allow it to squeeze in this tight rough site and perform a heavy lift. A main disadvantage of this crane is the need to transport them between the sites using low bed trailer truck. In the crane industry, the all-terrain crane is considered the luxury version of a mobile hydraulic crane. All-terrain cranes can be considered a hybrid between a mobile truck crane and a rough terrain crane. Another big selling point of this crane is its multifunctional capability to travel on all kinds of off-road terrain and also as well as down highways at top speeds. All-terrain cranes come with a high price tag compared to truck cranes due to their combined benefits of mobility on and off roads. They are best used in job sites with multiple lifting locations with no need for graded sites. They are incapable of pick and lift operations where they can lift a load and move with it in the air for a short distance. The only other crane capable of this pick and lift operation is a crawler crane. Some rigging operations require lifting really heavy loads, like whole parts of a structure. This is common in building restoration and bridge construction. In this case, huge lattice-boom crawler cranes are used and are supported by heavy counterweight blocks. These cranes are heavy and huge that they come in pieces to the site and assembled using other cranes. Their assembly operation is a critical construction activity in itself that's reflected in the project schedule and budget. Here's another use case of these heavy cranes, where this one is supported on a rotating ringer on a barge to lift a whole precast concrete bridge span. This table provides a summary comparison between the main mobile crane types. We can see their differences in the boom length, radius, lifting capacity, and travel speed. You can see that the all-terrain is beating the truck-mounted telescopic crane in all comparison categories. It's clear that the highest lifting capacity and lifting radius can be achieved by a crawler crane. Now let's see a simplified process for selecting mobile cranes for rigging operation and checking their lifting capacity. First, we need to identify the lifting job three main parameters: radius, weight, and height. The working radius is determined based on the site dimensions and logistics plan that shows the crane location, the pickup point, and the delivery point. The working radius will be the largest of the pickup and delivery radius distances. The second lifting parameter is the working weight of the load, which should include the load itself and any elements connected to the crane boom. This includes the hook block weight, the sling weight, and the load weight. The third lifting parameter to find is the working height, which corresponds to the same elements we consider in the working weight. The working height includes the heights of the hook block, sling, and the lifted segment. In addition, we add the elevation where the load will be lifted with enough clearance. For example, this tilt-up concrete panel is lifted from the ground and tilted up to its location. So its lifting elevation is very minimal compared to an air conditioning unit that's lifted on a multi-story building. Done with the first step in the process. The second step is to identify the direction of the lift with respect to the 4 quadrants of the crane. There are 4 quadrants around the crane: center of rotation, 2 overside quadrants, and over front quadrant and over rear quadrant. The load capacity of the crane depends on the quadrant position of the boom. Usually the crane has the highest lift capacity when the boom operates within the front quadrant. The third step is to select the appropriate beam length for the load that will be lifted. This is done by using the lift working height and radius to identify the boom length using the boom chart of the crane. For example, if a crane bragging operation involves a lift height of 140 feet and radius of 90 feet, the shortest boom length to satisfy these work conditions is 160 feet boom. In some cases, the lift height and h and radius r are not the direct dimensions between the crane and the load. Rather, obstacles in the middle, like power lines, can worsen the load parameters and increase the lift height or radius. The fourth step is to identify the safe lifting capacity of the crane after identifying its boom length. The manufacturer of the equipment provides the safe lifting information in usually a tabular format, like the one shown. However, there is no standard format for the lifting capacity tables or sometimes charts. For a pair of boom length and load radius, you can identify the ideal safe lifting capacity. These load capacities are governed by 2 failure types. The first failure is a structural failure in the boom that happens for a short lift radius. The other failure type occurs due to the loss of stability and tipping of the crane. This shown table differentiates the 2 failure types using a bold line, so the crane operator can understand the potential failure type limiting the lifting capacity. The shown capacities are for ideal conditions, and the operator should consider applying adjustment factors to account for adverse work conditions like wind and the dynamic impacts of load swinging and hoist stoppage. The last step is to check the suitability of the crane to lift the load safely. This is done by comparing the safe lifting capacity is more than the working load. Also, detailed accessibility analysis should be done to make sure that the crane can access its base location, have an adequate outrigger setup space, and can operate with no boom obstacles. Let's practice what we learned using this exercise of a rough terrain crane lifting a 34 feet tall concrete panel to a clear height of 74 feet. The dimensions and weight of the left accessories are provided with the left radius. We are given also the boom chart and the load capacity table of the crane. We need to determine the boom length for this left pickup and the maximum net weight of the panel to safely lift it. We need to calculate the working height by adding up the clear elevation of the panel location and the heights of the panel and the sling. They add up to 130 feet. With the radius value, we identify from the chart that the boom length of 140 feet should work. Using this boom length and the working radius, we can identify from the table the maximum gross weight to be 31,800 pounds. By knowing the weight of the lift accessories, we can calculate the net weight of the panel that can be safely lifted in such lift job conditions. Let's watch this video to see some crane accidents which we can use to identify some safety precautions during crane rigging operations. The video shows also some tower crane accidents, which we will cover in the next lesson. The crane accidents in this video happen due to either lack of stability or structural failures of the crane jib or the rigging cabling system. That was a brief learning about mobile cranes. I hope you have now an appreciation of the amount of effort that goes into planning, rigging, and lifting operations. In the next lesson, we'll see a lot of similar concepts when we learn about tower cranes. Until seeing you in the next lesson, enjoy your time.